Now we're going to look at some examples that use the three kinematic equations we derived earlier. And one of the things that people have a hard time figuring out when they start physics is which equation do I use? And part of that is you will learn from experience what does what, but what you can always do is look and say, what do I have and what do I need? And I need to have one equation that has those things and nothing else. The good part about this is if, for example, the short way to do a problem is to use this second equation here in blue, and you screw up and choose the third equation here in red, the answer that you get from this can be put in the first equation here in green, and you can get the right answer that way. So there's really no wasted effort. There's just usually a fast way that uses one equation and a slower way that uses the other two. In pretty much everything in this chapter, we're going to ignore air resistance. So when things fall, we're going to see an acceleration of negative 9.8 meters per second squared. We can, of course, use these same kinematic equations for other problems like a car in a drag race. And it's good to keep in mind that A is not necessarily equal to negative 9.8 meters per second squared in any other situation. So for our first example, we take a rock to the top of a tall building, drop it, and it takes 3.5 seconds to reach the ground. Reasonable questions that you could be asked are, how tall is the building, and how fast is the rock moving at impact? If you want to find out the building height, you can look at the fact that you know final position is the ground, which will set equal to 0. The initial velocity, since it's dropped instead of thrown, is 0, and the time for the trip is 3.5 seconds. Also, since this is a free fall problem, we know the acceleration due to gravity. What we want to find is xi, the initial height. If we look at the second equation in blue, we find that this is exactly what we want. We only have one unknown, and that's x initial. So we plug in everything we know, and we solve for xi, and we get 60.025 meters. For part B, we want the final velocity, so we can use that first equation. The initial velocity is 0. We know how long it falls. We know its acceleration. We solve this, and we get negative 34.3 meters per second. Now, what you could also do, you could use the third equation and combine what you were given with what you found in part A, which is the height of the building. If you do this, you can get the same answer. You plug in everything now because, again, you're down to only one unknown since you found xi. You plug this in, you get this square root, and notice here that you get positive 34.3 meters per second. The reason is the root of a quadratic equation, you've got two. You've got the positive root and the negative root, and your calculator generally just gives you the positive root. So it's up to you to remember that this thing is falling down, and we've chosen down as a negative direction, so this velocity should be negative. Second example, we can imagine throwing a rock straight up 15 meters per second from the top of a 35-meter tall building. Then we can ask things like how long does it take to reach the ground, what is its maximum height, how long does it take to reach that height, and what is its speed at impact. Again, you put what you know, the acceleration, the initial velocity, the initial position, and the final position. Again, we've chosen up to be positive and down to be negative. You're not required to do that. It's extremely common. You can make your own choice, but you just have to be consistent. The reason the initial velocity is positive is because we're throwing it in the upward direction, and we've defined the acceleration due to gravity as negative. So first, if we want to find the time, we use this long kinematic equation. We know everything here except t. This means we get a quadratic equation, and the standard form for this, the way math departments will write it, is ax squared plus bx plus c equals 0. First of all, we're using t instead of x. That's not a big deal. The thing that's a little bit more confusing, if you look at our quadratic, the coefficient of t squared is 1/2 acceleration. This coefficient is the a for the math problem, and it's unfortunate that it works out like that, but everyone who does physics uses this form, and everyone who does math uses this form. So we'll just have to keep in mind that the math department A is 1/2 of our acceleration. Therefore, using that math department notation, we get this if we want to find our solutions. If you have the fancier calculators, they'll solve quadratics for you already. If you have the cheap one like I do, you have to do this. you get two roots, negative 1.55 seconds and 4.61 seconds. We want the positive root, but it's important to keep in mind the negative root is not garbage. We'll find out what it actually means later. It's not what we want right now, but it does have a meaning. The maximum height question is ambiguous because I didn't say measured from the top of the building or from the ground. And if I did this on a test, I would hopefully remember to tell you top of the building or the ground. Otherwise, you can get away with either answer and I'll have to give you credit. Here I'm going to choose to find the height from the ground. So we use this equation and we put in v as our final velocity. We know that's 0 because at maximum height you have no more upward velocity. That's what defines maximum height. We have our initial velocity, our acceleration, x final is that max height, which we don't know, and xi is where you start, which is the ground or 0. So we work this out. If we wanted to find the max height from the roof instead, we'd replace that 35 with 0. Anyway, when we do this, we get 11.48 meters for xf minus 35, or xf is 46.48 meters above the ground. Also notice when you look at the kinematic equations, you only ever find xf minus xi. You can always rewrite wherever you have those two. You can always rewrite it to be a delta x because there is no such thing as absolute position. Okay, back to this problem. The part C, the way we can find the time to max height, we can just solve this. We set VF equal to 0 because we know, again, that'll be our velocity at max height. We know our initial velocity and our acceleration. We get about 1.53 seconds. The velocity at impact, one way we can do this, we can use this same trick, VF is AT plus V initial, because we found the total time and error from the quadratic equation, 4.61 seconds, and we get negative 30.18 meters per second. You also could have done this by figuring out the time to fall from 46.48 meters to the ground from 0 initial velocity and adding that to this time to max height. But this is a little bit more straightforward. Now, what does the other root of the quadratic equation mean? What if instead of dropping or throwing this rock from the roof, what if you were on the ground and you happened to throw the rock straight up with this speed, 30.18 meters per second, only positive? We can ask how long would it take to reach the roof. We solve that quadratic. Notice here we've got two solutions, positive 1.55 and positive 4.61 seconds. We actually want the smaller root for this question, but then we can ask how fast is it going at that point. When we solve for this, we get 15 meters per second. Notice that now we have the initial condition for our first problem. We're at the height of the roof, and we're starting off with a velocity of 15 meters per second. From that point, it will go on up. It'll reach the max height of 46.48 meters, come back down and hit the ground after 4.61 seconds. In other words, if we were to throw this rock at 30.18 meters per second from the ground 1.55 seconds before the original rock, the two would go side by side in the graph of height versus time. So this is our original. We start at 35, we go up to about 47, and then we fall back down to the ground. The one that we would throw from the ground at 30.18 meters per second, that's the full parabola. So this is the path from the ground up to the top of the building where it meets up with the original rock and they go side by side.